In this session, we're going to talk about using sensors for in-season nitrogen management and some of the fundamental aspects that you need to consider. So sensor-based nitrogen management has been around for a while. Here we have an example of a handheld unit. Now they sell much smaller handheld units, and that's really for constant rate, more traditional nitrogen application. What we're going to talk about is variable rate application, where you have the sensors on a sprayer or a spreader, and in real time you're adjusting your nitrogen rate to what the sensors are seeing. So when we talk about in-season nitrogen management with sensors, split application is the starting point. You have to be comfortable with that before you go down the sensor-based road. Basically what we're looking at here is a chart that shows the corn growth curve over time and soil nitrogen mineralization over time. And we have this rapid growth stage where the corn really takes off. And when we apply all our nitrogen down up front, that nitrogen is vulnerable for a longer period of time until the rapid growth stage. So what we want to do is put 20 or 30% of our nitrogen down up front, come in traditionally when the corn is at about V4, 12 inches tall, and apply the balance of our nitrogen that we think we need. And this exposes less nitrogen to loss pathways, so it's vulnerable for a shorter period of time and offsets our risk. So that's really the starting point. It's a great nitrogen management technique in its own, but you have to be comfortable with that before you can go down the variable rate and path. So numerous algorithms have been developed by researchers in the industry. Now with these technologies, you can even create your own nitrogen algorithm for the sensors. There are two distinct approaches out there to N-rate calculations. There's the use of yield prediction and response equations, and then use of response only. It's important that if you're going to use sensors that you understand what type of equation you're using and where your recommendations come from. So what do active sensors do? Well, they emit light typically in the red or near infrared wavelengths. Some of the original Green Seeker sensors shown here did 60 flashes per second and then averaged those measurements over each second. And then they calculate NDVI, the Normalized Differential Vegetative Index. And simply that's near infrared minus red over near infrared plus red. To get technical, that's just a data compression. You're combining two wavelengths into one number. And then we correlate these sensor readings to crop vigor and nitrogen need using these algorithms. Because we're using an active sensor that's mounted on the sprayer, you get light saturation, so sunlight conditions, atmospheric conditions, varieties, these things don't have as much of an influence on that sensor reading of red and near infrared. Now different sensors, and there's been changes over time, they're using a little different wavelengths and they may be near red edge or something like that, but generally you're calculating some sort of vegetative index like this. So NDVI, which is the most common vegetative index, has been around for quite a while. It correlates very strongly with plant biomass. It's almost the same as if you went out by hand and clipped a certain area of your growing crop and weighed it to see how much per acre biomass you've produced at that time when you sense it. Very similar is the simple ratio where we just take near infrared over that visible light, red or whatever wavelength. Some sensors do include the red edge, which is a little bit closer to chlorophyll measurement. So as we see here, we look and we see two different lines. The orange line is 100 pounds of nitrogen per acre was applied to wheat. We're sensing it at the Feeks 5 in a potted soil. And then the yellow line is 0 pounds of nitrogen were applied. And so we can see that in different wavelengths as we go across the visible and the near infrared spectrum, that we get a difference in plants that aren't growing very healthy, aren't very large, or don't have enough nitrogen. So we talked a lot about nitrogen responsiveness, and that's what we need to capture in a nitrogen requirement algorithm. And response can be thought of in two ways. We can have a response index, which is a ratio of a high-end reference area to a standard or low pre-plant nitrogen. So we go out at planting, say in a corn crop, and we have an area that perhaps we didn't put down any starter nitrogen. And then we have an area where we put extra. And then we treated the rest of the field with 20% of what we thought the crop needed. So maybe we went out with 50 pounds per acre of nitrogen, and then in the high-end reference area we put down 150 pounds. In the low-end reference we put down 0 pounds per acre. And so the ratio of those two is the increase in yield due to nitrogen. So with a response index of 1.2, we expect a 20% increase in yield with nitrogen. A sufficiency index, though, is kind of the inverse of that. It's the percent of the high level over the percent of the low level, and it's always less than 1. So it's the sufficiency relative to the standard practice. And it typically uses the base N rate. So we put that 50 pounds per acre out there, and we go to an area that looks a little yellow or weak, and how does it relate to the good area in the field? How sufficient is it relative to the best areas of the field? So when we look at a sufficiency index of 0.75, and if we had an expected nitrogen need of 200 pounds per acre, then 150 pounds per acre is the farmer practice. It can be calculated with NDVI or the simple ratio. So here we have a graph of the sufficiency index. And what we see is that we have a lower sufficiency index at the lower nitrogen rate, which is on the horizontal axis. And as we go up with our nitrogen rate, we approach sufficiency, or 100% of optimum. A few of the groups doing research with sensors have determined that the relationship of that response index of NDVI in season and the response index of yield is not a one-to-one relationship. What that means is, if I go out and I look at the response index for the high-end plot versus the zero-end plot, and it's 1.2, and then I take the yield measurements at the end of the season, maybe I got a yield of 30% higher, not 20% higher. So that's where the algorithm I've been talking about comes in. The algorithm is used to adjust the response index that we take in season based on research, local and local conditions, to calculate the nitrogen requirement.